Unit 10, Chemical Equilibrium 2. Children, in plus 1, you could have learnt Chemical Equilibrium 1. Chemical equilibrium means with something related with chemical reactions. Irreversible reactions, reversible reaction, two types are there. Suppose burning crackers. Once the crackers have been burnt, obviously you can't get back. It's a irreversible reaction. Reversible reaction means water has been evaporated. After that, on cooling, you are getting back the liquid water. It's a very simple example for reversible reactions. So, in chemical equilibrium, we are going to deal with reversible reactions. Suppose, let's consider one simple reaction. H2 plus I2 gives 2HI. You know that this kind of symbol represents reversible equations. Hydrogen combined with iodine to form two molecules of HI. The number in front of this will tell you the number of moles involved here. 1 mole of hydrogen combines with 1 mole of iodine to form 2 moles of hydrogen iodide. Here, two reactions are there, obviously. Hydrogen combined with iodine to form 2HI is called forward reaction. Then 2HI decomposes to form H2 and I2 is called reverse reaction. So it's very clear that all the reversible reactions are made of two reactions. One is forward reaction and another one is reverse reaction. Here hydrogen combined with iodine to form HI is the forward reaction. In the reverse reaction, hydrogen iodide decomposes to form hydrogen and iodine. Here they are asking that the very speciality is, I will tell one example. Suppose one hydrogen combines with oxygen to form water, two molecules of water. We are balancing like this. Suppose we are considering only one reaction takes place. Initially, you may have the reactant. After some time, you may have the product. You can't have the reactant after some time. It's very obvious. But in this case of reactions, you are having both the reactant as well as product. Because both the forward reaction and reverse reaction takes place simultaneously. That's why they are calling it as dynamic equilibrium. So they are asking three more questions. What do you mean? Why do equilibrium reactions refer to as dynamic equilibrium? The answer is, it is made of both the forward as well as reverse reaction. Both the reactant and product are present in the reaction medium. That's why it is called as dynamic equilibrium. This is one of the concepts which has to be learnt now. Suppose, let's go for one example. Suppose A moles of capital A. Children, the small a represents number of moles. Capital A represents a chemical species. It is reacting with another chemical, say BB. Now you are getting CC plus DD. In plus 1 class, you have learnt that Kc can be written like this. That is, concentration of product to the power like this. The square bracket indicates concentration. That is, number of moles by volume. Then it is concerned with D like this. So first the product concentration has to be written on the numerator. Now let's come back to the reactant. The reactant must be written at the new denominator likewise. Look here. The product occupies the numerator. Always left hand side of this equation represents reactant. Opposite side represents product, always, likewise. So the concentration of product must be written as the numerator, and concentration of the reactant must be written as the denominator. This is the basic thing. It is called Kc. Suppose this reaction has been taken place. Now let's go for the reactant. What are the reactant in this case? A and B are reactant. Small a is the number of moles of capital A. Small b is the number of moles of capital B. These two are reactant. Suppose RF, we are writing RF. RF means rate of forward reaction. Rate of forward reaction. Of course, this is the forward reaction and reverse reaction. Once again, let's say, in forward reaction, A combines with B to form C and D. In reverse reaction, C combines with D to form A and B. RF is called as rate of forward reaction. What they are telling is, the rate of forward reaction is directly proportional to the concentration of the reactant. Likewise, this is called law of mass action. The rate of reaction is directly proportional to product of the concentrations of the reactants. As I have told you, this law is called law of mass action. In order to cancel this proportionality, we are equating one constant by introducing Kf, where Kf is called rate constant of forward reaction. What is Kf? Rate constant of forward reaction. So, RF proportional, in order to cancel the proportionality, we have introduced Kf. So, RF equal to Kf into all this. This is called rate of forward reaction. So, rate of forward reaction can be written like this. Similarly, rate of reverse reaction can be written as Kr Cc Dd. Look here, in rate of forward reaction, we have written the concentration of the reactants. In rate of reverse reaction, we have written the concentration of product. What they are telling is, at chemical equilibrium, rate of forward reaction is equal to rate of reverse reaction. What is that? At chemical equilibrium is the main thing. At chemical equilibrium, rate of forward reaction is equal to rate of reverse reaction. That's why it is called as equilibrium. In chemical equilibrium, forward reaction rate is equal to reverse reaction rate. So instead of RF, shall we write this here? Instead of RR, shall we write this here? Shall we compare these two? Now I am writing Kf AA BB. Yes. Instead of RF, I have written this constant. Instead of RR, shall I write this expression? Kr Cc Dd. Now let's do this. Let's take A and B to opposite side. So both A and B will go to the denominator on the opposite side. Kr will go to the denominator of left hand side. Let's see this. Now I am taking these two to opposite side. Upper Kf and Kr has to be brought here. So Kf by Kr equal to, look here, I am bringing A and B. Now you have got the ratio between Kf and Kr. Look here, in plus 1 you have learnt the Kc. Now only I have told you, this is the Kc. So, shall we compare this with the Kc? So Kc is nothing but Kf by Kr. This is one important relation. Kc can be compared with Kf and Kr. Kc equal to Kf by Kr. We can write like this. In the examination, they will give any two values out of this, either Kf or Kc, and you can find Kc value. It's a very important concept as far as chemical equilibrium is concerned. For example, in your textbook, question number D18, they have given Kc value. In your textbook, you have to go for D18 question. That is, the title number D and the section D, number 18 question. That's why I told you D18. In D18, the very first question, Kc value is given. Now I am dealing the problem D18 based on this formula. Now I have explained one formula. Based on that, I am going to do one problem. So the formula is Kc equal to Kf by Kr. Of course, this is the formula. Based on this, I am going to do the problem. The problem number is D18. D is the section title, 18 is the question number. What they have given is the equilibrium constant Kc for one reaction is given. That is, children, very first you start to do the problem, you write data first. First you have to write data. Under the data you have to list off what and all have been given there. They gave Kc value. Kc value is 2.5 into 10 to the power of minus 2. Then the rate constant of the forward reaction is given. Rate constant of forward reaction. I told you, rate constant of forward means Kf. Kf is 0.05 s power minus 1. S power minus 1 is the unit of rate constant. I will come to that afterwards. Under the chemical kinetics, it will be explained. Now, Kc value is given as well as Kf value is given. Then, calculate the rate constant of reverse reaction. This is the question. So, Kc equal to Kf by Kr. Here, Kc and Kf have been given. You have to calculate Kr. So, shall you take Kr to this side and Kc to this side? So, what will happen? Kr will go there. So, Kr equal to Kf by Kc. Remember that it's a capital K and this must be small k. It's a capital K, of course. The equilibrium constant must be written as the capital K and rate constant must be written as the small letter k. Small adjustment according to this. Now, shall we substitute the value? 0.05. Kf value is 0.05. 10 to the power of minus 2. 0.05. Next to the decimal, you are having two numbers. So, 0.05 can be written as 5 into 10 to the power of minus 2 by 2.5 into 10 to the power of minus 2. I would like to tell something at this stage. While solving the problem, take all the decimal into the number form. Then only it will be easy for you to do the calculation. Okay. So what you are going to do? Whenever the decimal number comes, it has to be converted into the power. Okay. Now 10 to the power of minus 12, 10 to the power of minus 2. 10 to the power of minus 2 and 10 to the power of minus 2 gets cancelled out. You are having 5 by 2.5. What will happen upon cancelling? It goes by 2 times. So Kr equal to, that is rate constant of reverse reaction equal to 2. S bar minus 1, of course. This is the problem. It's a 3-mark problem. If you write data alone, then you write with solution. While writing the final answer, you must specify the unit. Unit is very important. If you forget to write the unit, some marks will be reduced, of course. So, while solving the problem, first you are writing the formula, then first you are writing the data, it's the very first one. Writing the data, then formula, then substituting all the values. Of course, finally, you have to write the unit.